In the last video, we looked at the three defining properties of determinants, that the determinant of the identity is 1 of any size, that the determinant will change sign if we interchange rows, and thirdly, we looked in detail on this little more difficult property, which is the linearity property. And there were two parts to this, the addition version of it, or the addition aspect of it, and the scalar multiple aspect of it. Then we used this second one, the interchanging one, to say that if two rows are the same, then the determinant is 0. And that really helps us find determinants of certain types of matrices very quickly. And as an application to understand these properties, we looked at how to find the determinant of a 2 by 2 matrix. And we got the answer as expected, AD minus BC. Now, in this video, we're going to continue and look at some more properties. Now, let me mention this consequence real quick. A consequence of when you have two equal rows, the determinant is 0. One consequence of that is if one row is a multiple of another row, then the determinant is 0. Let me show you why that makes sense. So this consequence, maybe I could say it like this. So if I had, 1, 2, 3, 4, 8, 12, and whatever this is, doesn't really matter. And I'm doing determinants here, I have to be careful, not square brackets, but vertical lines. Okay, now you can see that the second row is a multiple of the first row. It's 4 times the first row. I could actually use linearity to factor out 4 from the second row. And what happens? I get 1, 2, 3, 1, 2, 3, A, B, C. So there you can see 4 times. Now the determinant of this matrix is 0 because that has equal rows. 4 times 0 is 0. So if one row is a multiple of another row, then the determinant is 0. I think maybe now that's clear why that comes from that property. Now we do a lot of row operations. And one of the row operations we do is we replace a row by adding a multiple of another row to it. So for example, we can change the third row by adding some number t times the first row. This property says that if you do that, then the determinant doesn't change. So that row operation does not change determinants. Okay? These properties are really about row operations. Before I continue, let me go back one more time and talk about this row operation of interchanging rows. That row operation changes signs. Then part of the linearity thing is multiplying a row by a scalar multiplies the determinant by that scalar. So that's one of the row operations as well. Okay, so these two row operations actually change the determinant. One changes sign, the other multiplies by the scalar. But this row operation, which we use a lot in elimination to turn things into 0, this one actually doesn't change the determinant. Okay, so we're going to start with this 3 by 3 matrix. And we're going to perform this row operation. So we're going to take the third row and add t times the first row to it. So instead of g, we do g plus t times a, so that's g plus t times a, and h times t times b, and I plus t times c. There we go. So here we've performed the row operation. So this is the new matrix. Let's see what the determinant of this new matrix is. Now we're going to use linearity here. Here in this step, we're using linearity, the addition version. When you use linearity, you have to keep all the rows except one unchanged. So we're keeping the first row and second row unchanged in this breakup. And we're writing the third row as a sum. For example, this g plus 2a, g plus ta is written as g and then ta separately, and similarly with h and with I. And so really we have two determinants now, this one and this one. But in this next step we're using linearity again. We're using linearity on, let's focus here on this matrix, on this determinant, where we're factoring out t, and we're using the scalar version of linearity. Okay? Now what do you notice in this? When we do that, you notice something interesting. The first and third rows are the same, so the determinant of this second matrix is 0. And so what survives is the first determinant, and there you go. We got the original matrix back. So to summarize, if you take a matrix and you do this row operation of adding a multiple of one row to another, the determinant doesn't change. You get the same determinant. Okay? Let's actually, why don't we do this? We have the formula for a 2 by 2 determinant. Let's see if we can verify this. So here, let me start with 1, 2, 6, 10. Now, because of the formula we've established, we could say the determinant of this is 10 minus this multiplier is 12. You get -2. Okay. Now, let me replace the second row with, let's say, I don't know. What is a good operation? What do we usually do? We usually eliminate things. Okay, so maybe I should take -6 times the first row and add it to the second row. And we're changing the second row. What do we get? We get 1, 2, and then 0, and then 6 times, -6 times 2 is -12, plus 10 is -2. There we go. So, we did the row operation, we got a new matrix. But now notice, if I did the 1 times -2 minus 2 times 0, the answer is the same. The determinant did not change from this type of row operation. Okay, and that's very interesting. And that's very useful, because we use this operation so much for elimination, and it's a nice thing to know that the determinant's not going to change. In the next video, we're going to look at more properties that are going to help us understand determinants further and simplify our life when we're actually going to calculate a determinant.